thank you for donating to me 25 minutes of your attention at this marvelous time of day when lunch is also competing for your attention. So since I know that I'm competing with lunch, I'm going to try to be quick, exciting, or at least controversial, and last but not least, loud. If you look at my title, you see why I'm in the quantum session. Unfortunately, I have to make a confession. I'm not going to derive quantum mechanics. In fact, I'm not even going to talk about quantum mechanics a great deal. Because although I'm going to start deep in the midst of quantum mechanics, I'm rapidly going to reduce the problem I'm trying to solve to what is essentially a problem of classical estimation, or inference. In fact, it's worse than that. If you look at, if you look at the midst of my title, you'll notice some reserved words there that suggest that the classicality will extend beyond the classical quantum divide, and that I'm going to be using tools of shutter, classical statistical inference. Of course, needless to say, this is heresy. So, this is really remarkable. We've got all of the various circles of hell. The heretics, we're locked in burning stone coffins down here in the 6th circle of hell. Before you consign me to the 6th circle of hell, it gets worse. The alternative title for my talk is Confessions of an Apostate, or Why the Guy Who Introduced Bayesian Quantum State Tomography to the Quantum Information Community is suddenly showing up at MaxEnt and advocating a frequentist technique. Now this is worse, because while the heretics are just down here locked in stone coffins in the 6th circle of hell, the apostates are way the heck down here in the 9th circle of hell. Depending on exactly how, I might be betrayers of kin, locked head first in blocks of ice, betrayers of guests or benefactors, or even betrayers of country. We're forced to eat one another. Lunch will be soon. So I want to try to convince you that actually it's perhaps better than that. So my third alternative title is Hybrid Vigor in Statistical Inference. And the basic idea that I'm going to come back to is that there really are constructive ways to breed Bayesian analysis with non-Bayesian techniques and get powerful tools. And I don't know which circle of hell this puts me in. I would like to think that you would move me all the way up here to the virtuous pagans in the 1st circle, who I think are just struck with grief from a lack of Bayes' presence. You might argue that this is misogyny, and so I ought to be here with the lustful blown about by violent and endless wind, or something like that. But, okay, hopefully I've woken you up enough that I can actually present a little bit of mathematics. So let me start with my problem. Other than the fact that I have a broken leg, my problem is that I would like to be instrumental in designing a quantum computer, which somebody will build at some point. I'm being paid to help design a quantum computer that somebody will build at some point. Whether I would like to or not is sort of immaterial at this point. So I'm going to take as a given for the moment that quantum computers are useful, interesting, and cool. You can read about this in Scientific American, or you can ask the NSA how much money they're devoting to this. It's also very difficult, which is why it's taking all of that money, and we still haven't gotten really off the ground. Why is this difficult? Because a quantum computer, when we get around to building it, is going to be built like a classical computer, like my laptop or your iPad, out of lots of hardware components. Those hardware components come in 2 categories. We need to prepare quantum states, and then we need to apply a whole lot of quantum gates. And these hardware components can go wrong in a lot of different ways. Quantum mechanics is a richer theory than classical mechanics, and so it allows you far more ways to screw up. So some of these ways are correctable. If they are, we need to know which ones, how we are failing. Some of them are not. If that's the case, we need to go back to the drawing board and build new components. So we need to characterize these components. The accuracy with which you need to characterize them is upper bounded, or the precision I should say, by some number called the fault tolerance threshold, that's between 10 to the minus 8 and 10 to the minus 3. That's basically a failure probability. We're not actually sure where the number is. The point is, we need a lot of information about the components, and it needs to be very precise. And furthermore, because we're talking about spending a couple $100 million on putting this thing together once we get the components, we really don't want to screw up. So we want our characterization to be highly reliable. And this is basically my job, is to characterize quantum state preparations, quantum gate implementations with high accuracy, and I need to have a great deal of confidence in my result because I'm submitting them to essentially a customer who knows jack about what I do in my office or my colleagues do in their laboratories, but is going to be investing a great deal of money in future research. So before I talk about how I'm going to estimate this, and before I get controversial, let me just briefly summarize the aspects of quantum mechanics that I need for my talk. The things that I'm estimating are quantum states and quantum gates. A quantum state is a d by d density matrix. That means that it's a matrix that is positive semi-definite and has trace 1. The diagonal elements of that density matrix in any given basis form a probability distribution for some measurement. So this is a direct generalization, in fact, of a d-element discrete probability distribution. The only catch is it's non-commutative probability, which means different things to different people, so I just threw it in there to sort of fertilate you. I can also think of these mixed density matrix states as stochastic mixtures of pure quantum states with no entropy. So a concrete example of this, and the only one that I'm going to refer to at all, are the quantum states for a quantum bit. A classical bit would just have 2 states, 0 and 1, along with all of the convex elements of the simplex in between. A quantum bit also has accessible to it an uncountable infinity of distinct but not distinguishable pure zero entropy states. They correspond to all the points on the surface of what's called the Bloch sphere. All the points in the interior are mixed states. They are inherently unknown entropic stochastic mixtures of those various pure states. Now, quantum states can't be sampled directly, unlike probability distributions, which was the motivation for the work with Chris Ferry, where we were looking at classical epistemic models, if you will, much like Rob Speckens talked about, where you are not allowed to sample them directly. So what we do instead is we choose some tomographic measurement, named after the process of computer-assisted tomography in medicine. In this case, for the qubits, the standard measurement is to measure the 3 Pauli operators, sigma z, sigma x, and sigma y, which correspond to spin along 3 orthogonal directions for a spinning spin 1/2 particle like an electron. And we just deal with the sampling mismatch, the mismatch between what we're really trying to estimate, which is a point inside this sphere, and what we're measuring, which are basically coin flip observables, because all of the Pauli spin operators, if you measure them, as Philip pointed out on the first day, give you just one of 2 discrete results. So the result is that the data that we get, the measurement data, are just multinomial data. They're like rolling weighted dice, and you're trying to estimate the bias, except that they are constrained, because there are some probability distributions that you could imagine having that do not correspond to a valid quantum state. You have a quantum state space embedded within a larger probabilistic simplex. And I will simply state that there are some interesting issues that this constraint raises, but they're not very relevant for what I'm going to talk about today. The only other thing you need to know about quantum mechanics is a deep and cool fact that I'm not going to do justice to, which is that quantum gates, or processes, are d squared by d squared matrices that are isomorphic to d squared dimensional quantum states. And that's the last that I'm going to say about quantum gates. I'm just going to treat them as quantum states from now on because it makes it much easier. The estimators that have been used to date in quantum information science are all point estimators. There are a few of them, and I'm going to simplify into 3 basic categories. This is all background review, feel free to doze. The oldest are called linear inversion tomography. And this is the one where you take some data, You calculate the frequencies of those data, and then you say, aha, the probabilities must be equal to the frequencies. And from that, I can infer a quantum state. And the problem is that when I do this, I usually end up with a quantum state that actually lies outside the realm of valid states. It can't be taken seriously. Nonetheless, people in my field were taking this seriously for quite a while until they got sufficiently bothered. Then they went off and they talked to a statistician, and the statistician said, do maximum likelihood, and they said, hallelujah. And so we have been devoted to maximum likelihood for about the last 10 years because, wow, what a sophisticated concept. Maximum likelihood always gives you something that is a valid state by construction, because you maximize the likelihood over valid states. It frequently gives you something that lies right on the boundary, and so it implies zero probabilities for some measurement, which is a little bit hairy. The third technique, which I would like to think is gaining a following, is Bayesian mean estimation. And this is the obvious Bayesian approach of starting with a prior, updating it, and then reporting the mean of the posterior probability distribution, which is operationally well motivated. In this case, it's the Bayes estimator for relevant risk functions. And this gives you something that is inside the block sphere. And we can all go home now, except for one problem. Point estimators cannot, ever, support logical statements about the true value of the parameter. For the religious, true-believing Bayesians in the room, every time I say true value of the parameter from now on, please cite Di-Finetti and think about this as very, very long sequences of future events. These are the things that I want to make logical statements about. And thanks to Di-Finetti, we know that these are basically equivalent. But it's more convenient for me to talk about true values. If you put error bars, large deviation bounds, etc. on, you convert a point estimator into a region estimator. A region estimator does allow you to make such statements. So we can start with a point estimator and then put error bars on it, but this is sort of like putting wings on a car if you want to fly. It's not very efficient. So let's start from scratch and build an airplane, by which I mean an optimal region estimator. So region estimators are maps from data to regions of the parameter space. In this case, sets, preferably convex, of states. The two things that we want from a region estimator are, first of all, that the region that we report should contain the true state with very high probability alpha. And secondly, we want small regions that allow us to exclude lots of states, like the ones for which my computer would fail. What kind of region estimator we should use is an interesting question. We could make a very bad decision. We could use standard errors and bootstrap. This is what I would call the bad frequentist approach. You just sort of pull something out because it looks nice. I'm not even going to discuss this anymore, except to say that under certain circumstances, it fails horribly. If I want to take a Bayesian approach, I would report a credible region. If I want to take what I would call the good non-Bayesian approach, notice I've carefully avoided use of the word frequentist and good in the same sentence here. Then I would report confidence regions. So briefly, let me survey these things, since I've taken too much time in my introduction and need to race through the rest of my slides. A credible region estimator is exactly what you would think. You take your posterior, and you find some region that contains alpha of the posterior probability, and you report it. This has a beautiful interpretation. It supports the statement that the probability that rho is within the region you reported, given the data, is at least alpha. Of course, this requires a prior. And this is awkward for reporting results to funding agencies or journals because the correctness, the reliability of this statement depends on the prior's validity. If you believe the prior, you believe this statement. If you don't believe the prior, you don't believe this statement. I need something that I can report to my robotic masters in Washington, D.C., if you will, that they will believe. There's a more concrete problem beyond just the different subjective priors, which is that if you imagine that the parameter is chosen adversarially, this actually explicitly invalidates any given prior. In other words, if you know it's being chosen adversarially, you can't write down a prior because you know that it won't be distributed according to that prior. So the alternative to this is confidence regions, which are harder to intuit. But a confidence region estimator is a map from data to regions which satisfies this property. The probability that I assign a region containing the true state is, for every single true state row, for every possible state of nature, greater than or equal to alpha. And this holds for every possible state of nature, so it holds unconditionally as well. You could say it holds for every possible prior as well. There's no prior involved in the definition of this, which makes it reliable against adversarial choice of the parameter, but you can't say anything conditional on the data. The interpretation of this is that it's a machine guaranteed to work with probability alpha. Catch is, you'd never know whether it worked or not. So, very briefly, my verdict is that confidence regions get an A-, credible regions get a B. They both have laudable features. But I'm going to talk about confidence regions because they allow me to make statements that hold absolutely. And I will sort of briefly say that something I'm very interested in is the idea of region estimators that are both that provide both confidence and credibility. I'm going to skip this slide because it was just philosophizing. Okay, now I'm going to do a derivation, except actually, thank you, Ariel, for the inspiration, I'm going to skip the derivation. I'm going to derive optimal confidence regions. I'm going to start by demanding correctness. I'm going to try to achieve small regions. I'm going to try to minimize the volume of the regions that I assign according to some arbitrary measure d rho. Please keep this in mind. Pick any measure d rho that you want. It's just used to define volume. That's all. It is going to fall out of the problem in just a moment. Then I'm going to say, well, there's an expected volume for every given row. And then I'm going to grab an actual measure that means something, an averaging measure that I'll call P of rho d rho. And I'm going to minimize the average expected volume of the region that I assign over this measure. This measure matters. Is this a Bayesian technique or not? Is this P of rho d rho that I'm picking a prior? I'll let you think about that and tell me what you think. One answer is not really. It doesn't describe my beliefs. I don't claim that it describes reality. I don't believe it. I don't assume it. It's just a tool for assigning the power of my estimator. The other answer is, well, sort of, because optimizing the expected performance with respect to this measure gives me a Bayes estimator for that prior. So these priors, if I can do this optimization, which I'll do in the next slide, actually index the admissible estimators, the ones that cannot be beaten and are inequivalent to one another. Okay, so here's the derivation, very briefly, for designing optimal estimators. And feel free to ask me about this slide later on, but the basic idea is that if I represent an arbitrary estimator as a bipartite graph, where a given data set is connected to a given state, if and only if the region that I assign upon seeing that data set contains that state, then I can do a fairly simple analysis with only one ... that involves 6 trivial algebraic steps, just reordering integrals and summations. And I can find that in order to get correctness, I have to have the sum over all data sets connected to each state row of the probability of that data set given row at least alpha. That's just correctness. Think about it for a moment. And the volume that I'm trying to minimize is just the sum over data sets connected to row. Sorry, this should be an integral d rho. I'm just going to integrate this quantity d rho of the probability of d, unconditional. I've used my prior to define that. So I now have a pointwise optimization problem. For every single row, I just have to optimize to achieve this while minimizing this. And about 5 minutes of thought tells you that the optimal way to do this is to go down and each state gets connected to data sets in decreasing order of a probability ratio statistic. The conditional probability divided by the unconditional probability. I've seen this quantity show up at least twice, probably more than that, earlier in the conference. This defines a probability ratio confidence estimator. It's something you can actually do. And it is the Bayes estimator for any particular prior. I'll briefly point out that maybe the most important thing I'll say. What's the role of the prior? Suppose you pick a delta function prior. You're the experimentalist. You are absolutely certain that your experiment works. What happens is you get an estimator that yields slightly smaller regions than it would otherwise if that prior is true, and much, much larger, almost trivial regions if the prior is false. And it still has guaranteed coverage probability. The region that it reports includes the true state with probability alpha. So what happens is the funding agency is not on the hook. They get, the customer, if you will, they get a result that is true in the particular sense that confidence regions are. The scientist or the statistician is free to use whatever prior they want to put in their beliefs, but the penalty for being wrong falls on them. If they're wrong, they end up with useless, trivial results, but they don't report wrong things. So since I'm essentially out of time, let me just summarize the last step. You might say, well, what if I don't have any beliefs? The point of this procedure is you're welcome to use your beliefs, and I, as the ignorant customer, can still trust you. But if you really don't think you have any beliefs, or you're not sure what your beliefs are, you might as well guard against the worst case happening. And doing so leads to minimax, which I'm going to approximate by a heuristic, by essentially defending against bad worst case performance, against an adversary. And when I do so, I end up choosing a prior so that the probability of any given data set D is proportional to the maximum over all states of the probability of D given rho. This defends me against any true state. It also leads to likelihood ratio confidence regions, which have all sorts of nice properties in that, for one thing, they make frequentists happy, they satisfy the likelihood principle, unlike almost any other confidence region estimators. I think it's really beautiful that while this has been proposed before, I don't know of any existing derivation that shows optimality in this particular sense. So having started wanting to get here, I was very happy to end up here in designing a tool for quantum information science. So with that, I will leave you with my conclusions, and thank you very much for your attention.
Thank you very much, Robin. Questions?
This is more of a comment, because I need to think about this rather than question it.
Thank you.
It reminds me very much of difficulty I had in my career when I was trying to introduce Bayes methods to numerical analysis. And I basically got nowhere, because the numerical analysts insist on having hard-edged proofs and so on, whereas the Gaussian processes and so on all give me limits elsewhere. So basically I couldn't get past the funding agency. So what like your answer?
Merci beaucoup.
Other questions?
I guess lunch is winning.
Yes.
But with this approach, you should be aware that you can end up with recognizable subsets.
Sorry, say again?
You can end up with recognizable subsets, so the data clearly exclude the parameter estimate you have achieved. And that's also worrisome for the funding agency. If the funding agency can prove that your confidence region is not covering the parameters which lead to the data, then you're also in trouble.
I am not certain that I understand what you're saying, and I'd like to talk to you about this more. Let me, like Rob, answer a question that let me rephrase it as a question that I can answer. I mentioned that I'm interested in this hybrid vigor, and that in the future I would like to develop region estimators that are simultaneously supporting confidence, in the sense that they're machines that work with guaranteed probability against adversaries, and credibility, which means that from some Bayesian standpoint, not all, of course, but some, the region you assign is guaranteed to contain a certain fraction alpha prime of the posterior. Why is this so important? Why haven't I just fallen in love with confidence regions and gone over to the frequentist Kool-Aid? Because it is quite easy to define a confidence region estimator that occasionally returns empty sets. What the dickens does that mean? I am certain that the parameter doesn't exist. Of course, it's because the estimator is allowed to fail with probability 1 minus alpha, and sometimes it just fails and it takes its basis and goes home, like my 3-year-old sits down and starts crying on the floor. I failed! So this is why we really want to hybridize, and this is why the confidence regions only get an A minus. And I think this might be what you're referring to, that occasionally confidence region estimators can return just blatantly bad results, and therefore they can obviously be improved. And I'll conclude by saying these likelihood ratio regions never actually do that. So let me go out on a limb. Let me suggest that the hybrid regions that I'm looking for, that will make everybody happy by simultaneously being credible and confident, might actually be these or very close to them. And I may have not answered your question, but thank you for the opportunity to rant.
Okay, any other questions? Okay, let's thank Robin again.